Welcome everybody. Pleasure to announce our first speaker, PhD in Princeton and same Princeton fellow. Vice. So we are
but maybe you can hear me now. Perfect. So it's a pleasure to be here. It's been a great conference. It was a nice banquet last night. Thanks for all of you for coming immediately after the banquet, if you've come straight from Münster nightlife. So my title is Extremal and Near-Extremal Black Holes. So you might think that black holes are a pretty extreme thing already. So what are extremal black holes? But I'm not going to assume that you know anything about the subject. So I'm really going to hope to take it from the beginning, at least if this thing would work, which maybe it doesn't. Maybe I turned it off somehow. Let's see. Oh. What did I do? Okay, good work. All right, so I'll begin to explain to you what is a black hole. Nothing to be afraid of. It's a very simple, completely geometric object, and I'll explain it as such. And from there, I'll tell you, well, what makes a black hole extremal? What are extremal black holes? So then a fundamental question on which there's been some unexpected, surprising progress is the question of, can non-extremal black holes, the usual garden variety black holes, can they become extremal? After addressing this question, then I'll ask the question of, well, how exceptional are these extremal black holes, and what do dynamics of general relativity look nearby? And finally, time permitting, as an epilogue, I'll talk about a new picture of the moduli space of gravitational collapse. And this is a gift to Oscar because he wanted a moduli space somewhere. All right, so off we go. What is a black hole? So in order to tell you what a black hole is, I first have to tell you what is not a black hole. So this is good old Minkowski space. So Minkowski space, as many of us know, is sort of the metric that started it all. This is the geometrization of special relativity. So it's just the following metric on R4, which I've already conveniently written in polar coordinates. So minus dt squared plus dr squared, r squared times the spherical metric. And well, if we forget about theta or phi, or if you want to be all sophisticated, we sort of take the quotient by the group action by SO3, spherical symmetry, then you can think of this as sort of represented by the sort of half plane in RT. Okay? So what I've shaded here is just the half plane in the RT plane, okay, which is sort of the domain of this after you take the quotient. All right. So this is Minkowski space, but so Minkowski space does not have a black hole. We'll understand that very soon. But somehow, black hole is really something about the global geometry. So we really have to identify infinity. And the problem with this picture is, of course, that infinity is very, very far away. We can't see it, and we can't contemplate it. So how do we fix that? Well, first of all, trivial coordinate sort of transformation that you can do is you can introduce so-called null coordinates, u and v, so t minus r, t plus r. Well, if you compute the metric in these coordinates, then it's simply minus du dv plus r squared. Now you think of r as a function of u and v times the spherical metric. And of course, the significance of these coordinates is that so these are called null coordinates, and you should think that light rays, well, at least sort of radial light rays, they travel in the coordinate direction. Okay? So clearly, this is something related to the geometry of Minkowski space. And now you can do something which is extremely trivial, but at the same time very, very profound. And this is the following, that, well, okay, if you have these two coordinates, little u and little v, you can rescale them. So you can define big U and big V to just be some arbitrary, say, smooth increasing function of little u and similarly little v, such that the range of these functions is bounded. Okay? And of course, these rescalings, they preserve the fact that these are null coordinates. So they preserve the fact that radial light signals, they go on in coordinate directions. Okay? So if you do this, then the domain on which Minkowski space is defined becomes bounded, and so you can contemplate all of it. You can put it on the screen. It all fits. So this depiction is called a Penrose diagram, but so there are two fundamental things about this kind of depiction. So the one thing is you can read off causal relations. So in particular, you know your Lorentzian geometry. If this is a point here, unfortunately, my hand is still shaking from last night. But if you imagine that it wasn't, maybe I can. Okay, so that's really a point. Then we can read off the future of the point as we draw the line at 45 degrees. That's a constant capital U curve. We draw the line at 135 degrees from the horizontal. We shade in the region here. That's the future. Okay, so you can read off, let's say, the causal relations. Okay, and similarly the past, where you go backwards. Okay? But the other nice thing is there's this infinity now, so we can label pieces of infinity, and the most important part of infinity is what we call future null infinity. So this is this part of this ideal boundary of space-time, which is over here. And you should really think that these are ideal points, space-time, so they're at infinity, they're not in the space-time. They're infinitely far away, but they're also in the radiation zone. Okay? So you should think that, and actually it's those of you in PDE, if you solve the wave equation on this space-time, you can define the radiation field, and it's actually, you can think of this as a function on this future null infinity. So this is where radiation lives. But moreover, if you think already in the context of general relativity, where this is really the space-time in the vicinity of some massive system, okay, hopefully we're over here, as opposed to somewhere nearer to the body. Okay, so future null infinity is typically where we as observers sit. Okay, so now I can finally tell you why this doesn't have a black hole. Well, it's very simple. That's just the statement that if I look at the causal past of future null infinity, that's the whole space-time. And that's just the statement that, you know, sort of any point, to say it in the dual way, any point in the space-time can send a signal up to future null infinity. And you can read that off this depiction because, well, signals go at 45 degrees. Perfect. Okay. So I promised someone, I don't know, that there would be no equations. I sort of lied. We have to give lip service at least once to an equation. So this is not just some metric. It actually is the most simple solution of Einstein's celebrated vacuum equation. So it is a solution of the equations of general relativity. So these are just the equations that the Ricci curvature of this metric be 0, and obviously these are satisfied because this metric is actually flat. Okay. So this is actually taken from Einstein's paper, and it's literally taken from Einstein's paper, but at the same time, for the experts here, it's a deep fake, because Einstein actually used a slightly different notation for what we now call the Ricci curvature, which would have been very confusing in this talk. But fortunately, he used the notation R for something else, so I've actually pasted this together from his paper, and I can show you how. I did not use ChatGPT or anything. Okay, so very good. So this is sort of flat space, vacuum, nothing there, etc., etc. What about stars? So what do stars look like in this picture? So first of all, stars in general, like it or not, they have some matter. So they don't satisfy the Einstein vacuum equations, but they satisfy the more general Einstein equations coupled with matter. And okay, they can be written in this form. This is maybe slightly unfamiliar, but this is the correct form of the equations. And again, there's a little deep fake here, but this is also from Einstein's original paper. So what you should think is that there's some matter in some central region, and maybe there's vacuum outside. And actually, it was already Schwarzschild, maybe 2 months after Einstein formulated his equations, who found solutions to sort of this equation coupled with some matter equations. So it was equations of fluid dynamics. And well, you can also talk about the matter fields, but I'm just going to talk about the metric. So the metric actually looks like this. Doesn't really matter the details, where this capital M is a function of R. And you can write the metric again in some way in these null coordinates. And again, it doesn't really matter what the form is. You can represent the metric by such a Penrose depiction. That's what these depictions are called, if I didn't mention that. And the metric takes this. Okay. So one thing I should say is that, well, stars also, they're not black holes, and you can read this off from the picture because, well, this is exactly, again, the statement that it doesn't matter where you are, outside the star, inside the star, you can always go and send a signal to our friends at null infinity. Okay. So, so stars you should think are stationary solutions, but what happens when there's some dynamics? For instance, for stars to stay together, they need some pressure. What if you have matter that has no pressure? So there's really no stationary state. What will happen? Well, if you saw the movie Oppenheimer, then you probably noticed that in the movie, this paper actually appears. They're holding it at some point. So this problem was first addressed by Oppenheimer and one of his students, Hartland Snyder, in 1939. And well, in modern language, we would say that what they showed was that stars collapsed to a black hole. But actually, at that time, people didn't have the sort of insight of these nice little pictures that I just drew for you. So sort of geometric picture was not at all clear. It's very unclear, in fact, if you actually read this paper again. So people should not be blamed for not really understanding this for another 30 years. But 30 years later, things were understood much better, and we can draw the picture of what actually Oppenheimer and Snyder were trying to describe. And this particular depiction is taken from the famous textbook of Hawking Noahs. So this is the picture of a black hole. So, and again, you can realize this as a solution of the Einstein equations coupled to some matter, in fact, a pressureless fluid for the experts. It doesn't really matter the details. The point is that the spacetime will look something like this. And the claim is that, okay, so this, what's labeled r equals infinity, is actually what I labeled future null infinity. It's here. It is here. There it is. Okay? So future null infinity is here. Okay? But now we see that if we look at the past of future null infinity, it's everything to the south of a null line in this picture, which is like this, right? So all these points here, they cannot communicate to null infinity. That's the black hole region. Okay? So it's just the complement of the past to future null infinity. The set of points in spacetime that cannot send signals far away. Okay. And some terminology, so the boundary of that region, the past boundary of that region, or alternatively, if you want to think about it, the future boundary of the region that can send signals to future null infinity, that's called the event horizon. It's a null hypersurface and will appear in just. Okay. So I should say one other thing maybe that sort of, so this spacetime is, so it has some matter here, and this is the shaded region, but outside the matter, it's actually an empty space solution. So outside the domain of the matter, it actually satisfies these Einstein vacuum equations. And you can write the metric explicitly, and in fact, that explicit metric was written already in December 1915 by Karl Schwarzschild in a nice postcard that he sent to Einstein. So this is the metric. And you can ask the question, okay, let's forget about the star. What's the largest domain in which this metric makes sense? And well, sort of a priori, you might think this is problematic. This seems to blow up at r equals 2m, but that's actually a coordinate singularity. And sort of the largest domain the metric makes sense is actually a spacetime that looks like this. So again, this is the quotient by SO3. Okay? And it's sort of funny spacetime because there's two of everything. Okay, so it means the spacetime also has non-trivial topology. The spacetime topology is S2 cross R cross R. But in particular, this is a pure vacuum spacetime, and you can already talk about black holes for this pure vacuum spacetime. So in particular, I claim future null infinity now has two connected components here and here. We can look at the past. That's everything south of this V. So that's the region that can communicate with future null infinity, but there's something left. This is the black hole region. Okay, so that's very nice. So we can sort of talk also about black holes without having any matter. Okay, so that's convenient if you don't want to dirty your hands with matter. Okay, all right. So, okay, so that's what a black hole is. So now the next point is what makes black holes extremal. So in order to do that, we have to sort of generalize this Schwarzschild solution, and there are sort of two natural ways that we can generalize them. So the first way is we can add charge. So it turns out that Schwarzschild, you can think of it as a special case, sort of one parameter subfamily of a larger family of solutions, the so-called Reisner-Nordstrom solution, which are characterized by an additional parameter, this Q. Okay. Now these are not vacuum solutions; these are solutions of the Einstein-Maxwell equation, so they're coupled to electromagnetism. So there's also an electromagnetic field, which is sort of hanging around, but I only care in this context about the metric. And it turns out that this represents a black hole if Q in modulus is less than or equal to m. And if Q is equal to 0, this is Schwarzschild. Okay? So that's one way. So another way, which is so actually this Reiser-Nordström metric was discovered already in 1916, so very, very shortly after formulation of theory. Another way, which is less trivial, is you can add rotation. And so this solution was only discovered much later, in 1963, by Roy Kerr. It's a fascinating history, which we don't have time to get into. So this is a vacuum solution, so there's no matter. This is a vacuum solution, but it's not spherically symmetric, so it's harder to draw. Okay. Nonetheless, I'll sort of draw Kerr spacetime as if it were spherically symmetric. So I'll draw these pictures that, okay, strictly speaking, they only make sense at least the way I describe them in the spherical. And so this extra parameter is a rotation parameter, and this is a black hole metric again in the case where A in modulus is less than or equal to m. Okay, so the first example is a charged black hole, and the second example is a rotating black hole. And in the case where you have strict inequality and the parameters are non-zero, then the Penrose depiction looks like this. So it's different than Schwarzschild in a way that I don't really want to describe. But again, you can see that this has a black hole region because let's just practice. This is future null infinity. Its past is everything under this V, so everything left is black hole region. Okay. So you might ask, what happens when these parameters are bigger in modulus than m? Then you have something called a naked singularity. So I don't want to tell you what that is, other than it's bad. Bad. All right. So finally, let me tell you the following thing. So there's a quantity that I'm going to talk about in just a second, and it's sort of funny quantity. So you can look at this vector field dt plus, well, in the Kerr case, a over 2mr plus d phi, and in the Reiser-Nordström case, just dt. So this is the killing field associated to stationarity, and it's actually tangent to the event horizon. And you can compute that it satisfies an equation that it's tangent to the event horizon, but in general, it's not geodesic. And so its sort of failure to be geodesic is incorporated by this constant kappa. So you can compute it satisfies an equation like this with this constant kappa, which is non-negative, and is called the surface gravity. Okay. Anyway, in some sense, the details are not so important. It's some geometric property of the event horizon of the boundary black hole. So the reason I bring it up is the following. So in the extremal case, where the event horizon, where the sort of Penrose depiction looks somewhat different, again in a way that I don't really care to explain more in this talk. So the extremal case is characterized by two things. First of all, that you have equality here. Okay? So it's, if you want, the boundary between having a black hole, the black hole, and this bad thing that I don't want to talk about. But it's also characterized by this vanishing of the surface gravity. So that means that the killing field is actually geodesic on the horizon. Okay. All right. So this is what extremal black holes are, if you want. They are black holes. So again, make no mistake, this is again a black hole. This is future null infinity. We look at its past, it's everything. This is its past. There's more, so it has a black hole. All right. But it's special. It's special because it's sort of, if you go beyond this in parameter space, at least in these class of special solutions, you have this naked singularity, which is bad, but it's also characterized by this vanishing surface gravity. Okay. All right. So can non-extremal black holes become extremal? So this question goes back to a very influential paper written I guess 50 years ago, by Bardeen, Carter, and Hawking, the 4 laws of black hole mechanics. So let me just maybe read for you the abstract. Expressions are derived for the mass of a stationary axisymmetric solution of the Einstein equations containing a black hole surrounded by matter, and for the difference in mass between 2 neighboring such solutions. 2 of the quantities which appear in these expressions, namely the area of the event horizon and the surface gravity, kappa, of the black hole have a close analogy with entropy and temperature, respectively. This analogy suggests the formulation of 4 laws of black hole mechanics, which correspond to and in some ways transcend the 4 laws of thermodynamics. Okay, so this paper is a seminal paper because it introduced this analogy between thermodynamics, classical thermodynamics, and sort of black hole mechanics. Okay, so this is now called black hole thermodynamics. And so the 4 laws of thermodynamics, if you know about them, are confusingly labeled, numbered the 0th, 1st, 2nd, and 3rd. Okay, so I'm only going to talk about the 3rd. And the 3rd law, well, there are various formulations in classical thermodynamics, but the formulation that I want to sort of recall is the formulation that says that you cannot cool something to absolute 0 in a finite process. Okay, so this is one of the formulations of classical 3rd law of thermodynamics. So now I take a snippet from this paper, extending the analogy, since what I just said, even further, one would postulate it is impossible by any procedure, no matter how idealized, to reduce kappa to 0 by a finite sequence of operations. Kappa, again, is the surface gravity. So now if you think of dynamic black hole, all the examples that I've given are stationary. We now think of a dynamic black hole. It would be impossible to make this kappa turn it into exactly 0 in finite sequence. So this sort of cloud, this 3rd law paradigm, hovered over the subject for many, many years. And basically the image of what should an extremal black hole represent in the theory that was suggested by this paradigm was that it's really a physically inaccessible ideal limit. Okay? It's something maybe you can get close to it, but you can never actually achieve it, at least in finite. Okay, so so there's another reason you might want this to be true, other than the analogy with thermodynamics, and this is again taken from the paper of Bardeen, Carter, and Hawking. Another reason for believing the 3rd law is that if one could reduce kappa to 0 by a finite sequence of operations, then presumably one could carry the process further, thereby creating a naked singularity, which is bad. If this were to happen, there would be a breakdown of the assumption of asymptotic predictability, which is the basis of many results in black hole theorem, etc., etc., etc. Okay. So, yes. Well, I'll maybe sort of explain that in just a second. Okay. It's a good question, actually. All right. So anyway, remember, in parameter space at least, these solutions lie at the border with naked singularities. Naked singularities are bad, so maybe if you could achieve this, why can't you achieve a naked singularity? That would be bad, etc. Okay, so this was the paradigm, but a very surprising result, which was achieved in the last, I guess, around a year ago, by Christoph Kehle, who's at ETH, and Ryan Unger, who's a graduate student at Princeton, is that, well, this 3rd law is just false. And so let me state the theorem, and then maybe the theorem should also address what's commonly understood by infinite operations. So the theorem says that, no, I mean, you can do it. I mean, it's that simple. So in particular, you can take an impeccable sort of Einstein coupled with Mather system that's very well studied in the literature. So this is, in some sense, the simplest system where you can study this problem in spherical symmetry. So Einstein-Maxwell charge scalar field. And you can cook up initial data. Okay, so you can cook up initial data, which has the following property, that the black hole, that the data collapses to a black hole, so it's sort of like this Oppenheimer-Snyder space-time. So it's a dynamically forming black hole. All right, so this is future null infinity. This is its past. So you can see there's an event horizon. There's more. The more is the black hole. But at early times, okay, and by time, here it's important that you always think of advanced time. So this is, you should think of this as that coordinate v, okay, because that's the time that moves along the event horizon. Okay, so it's actually an exactly Schwarzschild black hole in the neighborhood of sort of this region here. And then at some later time, and thereafter, it's an exactly extremal horizon. So finite operations sort of was interpreted actually subsequently to that paper by Werner Israel in a famous paper. Again, this meaning that you could cook up initial data such that this happens in finite advanced time. So that just means that there really is a region like this, which is exactly extremal rise of Nordstrom up until the event horizon. Okay? So in particular, the surface gravity becomes, here it's positive, and then it becomes 0. Note, there's something disconnected in this picture. I don't want to talk about it more. That sort of was the subtlety that somehow in various arguments that had been advanced in favor of the third law was missed. But I really can't talk more about why this is. Okay, so the third law is just false. So given that the third law is false, given that these things, they actually occur, we need to understand more, okay, how exceptional are these and what does dynamics look like nearby? In particular, remember this fear, the fear of naked singularities, so this is a justified fear. Okay, so this brings me to the next topic, which is how exceptional are extremal black holes, and what do dynamics look nearby? So in order to understand this, it's maybe good to first go back to Schwarzschild. Okay? So remember that the Schwarzschild metric, okay, is also a special case of the larger curve family metrics. So you might ask the same question for Schwarzschild, namely, how exceptional is Schwarzschild in the whole space of solutions of the Einstein equations? Namely, suppose you perturb Schwarzschild ever so slightly, sort of what happens? Okay, is it stable? What happens? What is sort of how exceptional? Okay, so for this we have a theorem from a few years ago. This is joint work with Gustav Holzhegel, who is here, and also Igor Rodnyansky and Martin Taylor. And the statement is that Schwarzschild is as stable as it possibly could be, and I'll explain these words in just a second, in the full sort of dynamics of the Einstein vacuum equations without any symmetry, the full nonlinear dynamics. So what does that mean? So first of all, how do you set up dynamics? So actually, you can start this problem, so you can think of Schwarzschild. Of course, if you remember those pictures, you can think of Schwarzschild as arising from initial data, which has two asymptotically flat ends. But it's actually completely standard now in this field how to go from such initial data to data which is defined on two later null hypersurfaces. Okay? So in some sense, you should think that the problem starts here. So you should think of the exact Schwarzschild solution, at least the region of it that we care about, as being determined by null initial data that look like this. So you have a null cone. So upstairs, this is actually a cone. Remember, this is a quotient. Downstairs, it's a line. Okay? So this cone goes out to null infinity. This is actually an infinite cone. Okay? Its cross-sectional area is going up to infinity. This is actually a finite cone. Right? But in the domain of dependence of this, you have the whole sort of interesting region of Schwarzschild. So you have the whole future null infinity and the whole event horizon. So Schwarzschild is an explicit solution from some explicit initial data for the Einstein equations, this Ricci curvature equals 0. So now you can look at completely general initial data, which is close to Schwarzschild without any symmetries. General relativity has a well-posed initial value problem, so you can at least locally solve those equations. Right? So the question is, what happens globally? And the statement is the following: that so if we name the sort of the whole space of initial data this mathfrak M, so anytime you see mathfrak, scary, 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 this is a moduli space. It's some huge infinite dimensional thing because it's the space of all initial data for the Einstein equation. So in that space, the statement is the following: there is a codimension 3 submanifold such that if you lie on that submanifold, okay, then your initial data will actually asymptote to another Schwarzschild solution as time goes to infinity outside the black hole, and you'll be, again, bound by an event horizon. And if you don't lie on that codimension 3 submanifold, you won't. So why is this the best possible result? If you think about it, well, we know that Schwarzschild is one parameter subfamily of the curve family. We know that already. So we know that there are ways to perturb Schwarzschild so that you leave Schwarzschild. Okay, and this theorem says that, well, that essentially that is the only in the full infinite dimensional moduli space, that's sort of the picture. That you can perturb to Kerr, okay? But otherwise, you're stable. Okay. All right. So let's keep this theorem in mind, because the question is, could a similar statement hold for extremal black holes? This would be the best case scenario. Okay. So one point I want to make is, why is this number 3 and not 1? Why is it codimension 3 and not codimension 1? Well, this has something to do with how you parameterize moduli space, given the fact that Schwarzschild is sort of more symmetric than the Kerr family. Okay. So anyway, I don't want to get into that, but I claim this number is the sharp number. Okay. All right. So it turns out there's a problem, however, with this very optimistic scenario that whatever is true in the Schwarzschild case, exactly the same scenario is true for extremal Kerr, and that is the so-called Aretitis instability. So it was discovered around 10 years ago that all extremal black hole horizons, they suffer from a certain instability. Okay? So something funny goes on at the event horizon, and it's a purely geometric effect in some sense. It just has to do with the fact that the surface gravity vanishes. And it's true on any sort of extremal horizon, any extremal horizon you could think about. So that's a problem. So you might think that, okay, this means that these things are unstable, case closed. But that's not the case. And in fact, there's a very recent result, at least in the Reisner-Nordstrom, extremal Reisner-Nordstrom case by a postdoc who is here, Marius Petroaia. So I've purposely made this snippet very, very small, so you're not tempted to actually read what it says. But the point is that there is a theorem. It says theorem somewhere. Theorem. And basically, the theorem says the following. First of all, this instability, it's true not just for the linear wave equation, which is actually the setting where Aretaikis first found it, but it's true for the linearized Einstein-Maxwell system. So it's there, but it's always somehow compensated. That's to say, you have some quantities that they grow on the horizon, but they're always somehow compensated by some other quantities that decay. And they're compensated in a way that you might hope you can still prove stability, nonlinear stability, okay? But maybe, all right, something funny happens on the horizon. So that's great. It turns out that in the extremal Kerr case, the situation is even more complicated, because there are worse instabilities associated to extremal Kerr than to extremal Reisner-Nordstrom. So I don't want to get into details, but there's some important work of Day and Gajic on that. And in fact, embarrassingly, right, so I still have that typo. So embarrassingly, we still don't know the answer to the following question. Look at extremal Kerr, okay? Look at the simplest linear wave equation you can imagine, and you should think linear wave equations, this is a model for the linearized Einstein equation, okay? Are solutions bounded for all time on the exterior of the black hole region? So that question is open. So this should read extremal. Okay, so that question is open, and the best known results currently are due to Rita Teixeira da Costa. Okay. All right. So given the situation in that paper with Holzhegel, Rodniansky, and Taylor, we made a little conjecture, and actually because of this difference between the extremal Reisner-Nordstrom case and the extremal Kerr case, because there's a lot of uncertainty what happens in extremal Kerr, we chickened out of making any conjecture for extremal Kerr. We only made a conjecture for extremal Reisner-Nordstrom. But somehow that's harder to state, and there's no reason to chicken out here in front of an audience that maybe. Anyway, so let's be brave. I'm going to change my conjecture and make it for extremal Kerr, which is sort of easier to read. Okay. So the conjecture then is the following. So let's again think of extremal Kerr as arising from null initial data, just like we thought of Schwarzschild. So there's some explicit vacuum initial data that leads to this funny extremal black hole. Okay. Now let's look at the moduli space, this scary space of all nearby initial data, this infinite dimensional space. So the statement you might hope for is the following. There should again be a codimension 1 submanifold, which I'll call M stable. such that if your initial data lie on that submanifold, then your spacetime will asymptote to a nearby, again, extremal resolution. And because we have to make lip service to this Aretakis instability, but okay, generically, for generic initial data conditioned to being on M stable, then something funny will happen on the horizon. So now in the physics literature, there's a lot of actually work on this Aretakis instability subsequently to that discovery. And so this is called horizon hair. Okay? So generically on M stable, you'll grow infinitely much horizon hair. That would be very useful for me. Yeah, I should visit this moduli space. Okay. So, all right. So let's believe in this conjecture, because you might think that in such talks one should always believe any conjecture and move on. So let's believe that that indeed there's this codimension 1 submanifold in moduli space, sort of, which represents black holes that become extremal. Since it's codimension 1, you might think that it separates two regions of moduli space. So what should it separate? And well, we write in our paper. Moreover, one could hope to prove that this submanifold M stable delimits the boundary, signifying a phase transition between two very different open regions of moduli space. So first of all, the set of data leading to spacetime is failing to collapse, and the set of data leading to a black hole exterior settling down to a sub-extremal pair. So what's the picture to have in mind? The picture to have in mind is the following. So this is moduli space now, okay? And this is this codimension 1 submanifold M stable, okay? And somehow on one side are spacetimes that actually collapse to sub-extremal black holes. Okay? So that should be an open set. We believe that those are stable, okay? And on the other side is the following. So remember, this is this funny thing. The initial data is actually finite. Okay, so this cone is actually a finite cone. So it's very remarkable that in some cases, for some initial data, you have an event horizon. So even though this is finite, the time at infinity is infinite. Okay? But if no black hole forms, then, okay, the solution will just look like this diamond. This will be infinity, but you'll run out of time at infinity. And you won't know what happens later because I didn't tell you more data. So as far as data is concerned, this is the most that you can ever say. Okay. So actually, what's also interesting is a sufficient condition to lie on the right-hand side is the presence of a single trapped or marginally trapped surface in the data. So this is a statement for experts. In particular, this tells you that something called overspinning scenaria, which are much discussed in the physics literature, they cannot happen. This also says that you shouldn't worry about naked singularities. There are no naked singularities in what I just said. So extremal black holes are not an entrance drug to naked singularities, but it's the border between forming a black hole and failure to collapse. Okay, so in the final 3 minutes, in the final 3 minutes, let me very, very briefly give you an extension of the story, which is very, very interesting, and in some sense sort of goes beyond this issue of, in what I've talked about now, I've only given you, in essence, a little bit of initial data. I haven't told you the whole initial data because I only had a finite cone. So, and this is this new picture of the moduli space of gravitational collapse. So, a very influential paper for understanding what the general picture of gravitational collapse looks like is this survey paper of Gundlach and Garcia. And in this paper, there's a picture of what one could call the moduli space of gravitational collapse. So all sort of solutions of the Einstein equation starting from one-ended asymptotically flat initial data. Okay? And well, the picture they draw looks like this, but because I don't want to explain their picture, I'm going to explain to you my picture. So this is my redrawing of this picture. And so what is this picture? So this is, every point is a space-time, but if you prefer, you can think of, spacetimes are parameterized by initial data, so every point is initial data set, if you prefer. So in the middle is Minkowski space, the spacetime that we started with. Okay, so that's a solution that has no black holes. So in my language, it disperses, means there's no black hole. Okay, and actually, Minkowski space is itself stable. This is a celebrated theorem from the 80s by Christodoulou and Kleiner. So that means that there's an open set in moduli space around Minkowski space, such that the solutions also disperse. Okay. On the other hand, we know that there are solutions that form black holes. So, for instance, Oppenheimer-Snyder. So here, let's say, is a solution which forms a black hole. And Choptuik, in a very influential paper, he looked at one-parameter families of initial data that interpolate between two such solutions, and he studied these one-parameter families. And what he showed is that, well, there's a critical value of the parameter, no matter sort of how you try to choose these families, such that you neither disperse nor form a black hole. And what you get there is exactly a naked singularity. Actually, none of that has been proven. It's an important open problem, but that's what he sees numerically. So in physics, the traditional moduli space that they draw looks exactly like this. You have a sort of an open set around Minkowski space of dispersive spacetimes. Way out there, you have the spacetimes collapsing to black holes, which is again an open set. And then on the boundary, you have critical naked singularity. Okay? Moreover, in this picture, you should think of this boundary as codimension 1. So naked singularities, they exist, but they're exceptional, at least. And they exist exactly in the boundary between forming a black hole and not forming a black hole. Okay, so this picture is great, but very, very recently, a few months ago, the following remarkable theorem was proven by Kayla and Unger, an extension of their other work. And what they showed is that it's not just naked singularities, but extremal black holes, they also occur precisely in this way on the boundary of the black hole region with dispersing fluid. So what they construct for a very sort of vanilla Mather model, so an impeccable Mather model, is a one-parameter interpolating family of solutions between Minkowski space and some solution that forms a subextremal black hole, such that there's a critical solution which forms an exactly extremal black hole, in fact, in finite time. And then to the right of this is dispersing spacetime. So what this suggests, and this is my final slide, essentially, is the following. The picture of moduli space that we see in the physics literature is actually naive. So yes, there is sort of some of the boundary between dispersive spacetime and black hole solutions may indeed involve these critical naked singularities, which after all have been seen numerically. But there actually is another portion of this boundary which may represent critical extremal black holes. And if you believe the conjecture, which I stated previously, then this boundary could be a regular, codimension 1 hypersurface in the moduli space. In fact, let me just sort of say this final point. So if we compare these two squares in moduli space, just to go back to this, and I'll finish. So you should think that the squares I just draw are this square, right? But you see, from the point of view of if I only know the data on a finite cone, I don't know if this will collapse later or it will actually disperse. And indeed, in moduli space, the claim is you can see both phenomena. So here is the case where you have this. So this blue segment is non-critical extremal black holes. Again, codimension 1 piece of hypersurface. And both to the right and to the left, you have subextremal black holes. But let's say to the left, the collapse happens later. Okay, not in the domain of dependence of that cone. Whereas here, you genuinely, now to the right, you don't collapse. You disperse. So this is the new picture, conjectured picture of moduli space. There are many young people in the audience, so maybe one of you will prove that this is actually the truth. Thanks a lot for your attention.
Thanks a lot for shedding some light for us on black holes. Are there questions? First ask. Are they
That's
correct?
that's a very good question. So famously, the second law was proven by Stephen Hawking. This is the famous area theorem. So if you remember the analogy between thermodynamics and black hole mechanics, so entropy corresponds to area of the event horizon. So the statement is that the area of an event horizon has to be uh, non-decreasing, um, and this was proven by Stephen Hawking, who sort of also realized, the significance of this fact. And it's actually quite elementary. In some sense, it's an application of the Raishaduri sort of type equation, so equations that differential geometers know very well. There's also the zeroth and the first law, which, okay, maybe I won't say it in more detail, but they do have, they're somehow they have less domain of applicability, but in their domain they are well established. So it was really the third law which somehow, yeah, was not established and now has been falsified.
You have some gravitational waves
Yes.
coming in. Would you be able to detect whether they came from an extremal black hole?
Yes, so that's a very interesting question, one which is of now great interest in sort of theoretical physics and in astrophysics. I should say, by the way, that these extremal black holes are, so remarkably for reasons that are not understood, so astrophysically, it is believed that many black holes that are observed are very near extremality. Of course, one should take with a pinch of salt anything you hear from astrophysicists currently, because the story often changes, but that's sort of the current story. They're also interesting from the point of view of high energy physicists, and in some sense the charged case is a play tool for high energy physicists and various speculations, whereas the rotating case, you should think of this as real astrophysics. In any case, so in real astrophysics, indeed, they are very interested in, is there a signature of extremality? And in fact, there's a remarkable connection between this horizon instability, this Aretakis instability, and signatures at null infinity. So there's a remarkable connection between things that are only happening on the event horizon. So you would think you cannot observe this if you're not on the event horizon. Believe me, you don't want to be on the event horizon. But there is a connection between those and things that happen at infinity. And so, yeah, so this is something which is being studied, and you can actually prove theorems about that. So that's work in progress. So Aretakis and some of his collaborators, Gajic, they have some results on that, and there's also some numerics.
So if you go back to the picture with the moduli space and the critical boundary, yes, that one.
Yes.
So you have parts of the boundary where you say you get an extremal black hole, and and parts of the boundary that where you get a naked singularity.
Yeah.
Could those happen on the same connected components of the boundary?
So that's what I've drawn, but it's a very good question that you ask, because we have no idea. In particular, so I claim that it's reasonable to expect that the dispersive region is connected, but there's no reason to expect that the black hole region is connected. Okay, so in particular, it could be the case that actually this is not quite the way the picture works, but you have islands in the dispersive spacetimes, and maybe sort of, so maybe indeed this is a different connected component. I instinctively don't think so, but we really have no idea. We need topologists to sort of tell us about the topology of. I mean, the most basic questions are completely open. If indeed it is like I drew it, then obviously, okay, this, maybe this is a codimension 2 hypersurface of some special, we have no idea in reality. It would be certainly very interesting to probe these regions. There's also a reason that I've sort of drawn it non-star shaped, but let me not go into it. But in reality, this is speculation, and we know very little. What we do know is that sort of this original picture was naive and is not correct. But yeah, I mean, it's very there are many aspects of this picture which would be very interesting to know anything more.
For the
So this one parameter family, is this very explicit, and is there a possibility to branch at some point from this family?
So the family is very explicit, although it is not elementary to construct, but it is finally explicit. Yeah, I mean, what would be potentially possible, for instance, is in order to probe also that kind of question is now to take a family of such families and maybe try to see if indeed you can access sort of this point, for instance. Yeah, would be great.
forceful and stop here. Everybody else. Thank you very much.
Thank you.
The second speaker. Ah, yeah.